My name's Matthew Garrett. I work at Google on various internal security-related things. What I'm talking about today is not any sort of official position of my employer. You may be able to guess that as we go along. So for some background, I've been working on firmware for a while now. My first LCA presentation was on ACPI back in 2006, and things have just been getting worse from there. Today, rather than talking about how specific aspects of firmware are terrible or poorly implemented or just otherwise bad, I'm going to be focusing very much on the security of firmware itself. So when we're talking about security of systems, we often only look at the layers of the software stack that are easily visible to us. We tend to ignore a lot of the underlying detail, partly because it's, as previously mentioned, scary and bad, but also because it's largely hidden from us by the kernel and other components. So to begin with, we need to define what firmware really is. So computers have one core competency, which is executing code. Everything else they're terrible at. Running code is basically the only thing that you can trust a computer to do. But there's some irony in the fact that when you turn a computer on, it's not very good at running code. Those of you who were in Stuart's presentation earlier will have heard some of the ways in which you have to really cajole a computer into getting to the stage where it's enthusiastic about running code, which is an understandable position to hold. So firmware is the code that is responsible for getting your computer into the state that we would generally recognize as being a computer. Firmware is responsible for stuff like making RAM work, which is a pretty fundamental part of the entire process. But a computer that is only getting to the stage of initializing itself to the state of being able to run code is still not particularly useful. That's basically equivalent to the Commodore 64. You turn it on, and excellent, you've got a prompt, and now it's time to write your own bootloader. So firmware these days gives you the interfaces that allow you to actually run the code that's then going to load the rest of your operating system. Firmware also abstracts away various details of hardware on some platforms. Some machines, there's no firmware, or there's a very thin layer of firmware that still exists after system bring up. On other systems, there's quite a lot of firmware, and that firmware is responsible for hiding the fact that hardware vendors keep changing how things work and not telling you. And just fixed up in firmware, the correct interface uses the firmware makes it all work. And finally, one that people don't often realize, firmware is often considered to be in some sort of privileged position in terms of the overall system. Firmware on x86 platforms is able to access certain hardware resources that can't otherwise be accessed. It's there to mediate access to those resources. So for instance, system management mode, which I'm going to get onto later, is responsible for permitting you to write to the flash chip on your board. And this prevents the operating system from just being able to overwrite your flash, which means it also prevents malware from being able to just overwrite your flash. But there's something that all of these things have in common, and that is that fundamentally firmware is code, which is good because otherwise it wouldn't run. But the downside of its being code is that human beings are not particularly good at writing code. A significant portion of the time, while we're sitting there writing code, we're actually writing bugs. You would not believe how many bugs I can write in a minute. And give me a few hours, yeah, I'm very good at it. So code contains bugs, which means your firmware being made of code almost certainly contains bugs. And this is increasingly true as firmware becomes larger, firmware brings new features, and firmware just does more. There's a lot more code. The number of bugs per line of code remains relatively constant, so adding more code tends to mean adding more bugs. But why do we care about bugs in the firmware? Fundamentally, this comes back to the things the firmware is responsible for. The firmware is there to make your computer work in the beginning. It's there to then give you the interfaces you need to boot an operating system. If your firmware ceases behaving in a trustworthy manner, if your firmware starts executing malicious code, you can no longer trust that any of the rest of the code that runs on your system is itself trustworthy. You're now in a situation where your firmware can compromise your bootloader can compromise your kernel can then inject backdoors into other bits of code. And this isn't some hypothetical. We've seen firmware-based rootkits that are in the wild, that are used to attack operating systems, such that even if you do a clean reinstall of the operating system is still compromised. Even if you switch out the hard drive, the system is still compromised. So firmware security is a real concern. It's not just some hypothetical. So you might be thinking, well, OK, what's the attack surface for firmware? How does an attacker actually take advantage of any of these bugs in a way that allows them to do something malicious? And something I haven't really mentioned here is that, well, obviously, firmware is generally contained on a small chip on the motherboard. Someone with physical access to the system is potentially able to just directly tamper with the firmware. So physical access is an attack surface. That's something that we can't do a great deal about by writing more code. So it's largely out of scope here. So far, the industry approach to handling the physical access portion of things is either don't execute the firmware unless the firmware has a valid signature, which is what Intel's BootGuard technology does, or alternatively, have the firmware be measured into some sort of TPM-type device at boot time. So you are potentially still executing malicious code, but you're able to determine after the fact that the code was malicious. But otherwise, firmware still has to deal with stuff. Firmware has to be able to load your bootloader. And that means it needs to take code and put it somewhere, and potentially parse some of that binary and then execute it. So in the old days on BIOS-based systems, this wasn't so much of an issue because the way we executed the bootloader was that you just took a disk, you read the first 512 bytes off the disk, and then you just jumped into them. I'm sorry, Slack has suddenly decided to demand attention. This is what I get for running proprietary software. OK, so in the old days, not so much of an issue. Binaries were not something that were parsed by the firmware. These days, your bootloader is a PE-COF object. The firmware needs to take this file, potentially even verify a cryptographic signature on it, relocate it, and execute it. And that's a lot of stuff to do. And giving something a suitably malformed binary is potentially a way to get into a path of code execution you shouldn't be in and cause bad things to happen. Systems that are able to read bootloaders off file systems as opposed to just off raw disk or flash also have to parse the file system. But also, there's frequently a bunch of runtime interfaces that are presented to the operating system by the firmware, so the operating system is able to make use of the firmware to do various things. This isn't some sort of, so it's very easy to demonize UEFI here. UEFI does provide an interesting number of runtime services that have quite a lot of code behind them. But who here ever programmed for DOS? Wow, I'm so sorry. That's a lot of you. Right, so you remember making BIOS interrupts. Right. So doing things in DOS meant calling int whatever. That's all runtime firmware code. Now, generally speaking, in DOS, you didn't really care whether your firmware was insecure in terms of if you called a certain interrupt with sufficiently invalid arguments, it might write to arbitrary memory. Because it was DOS, you could just write to the arbitrary memory yourself. But those interfaces still exist on currently shipping systems. If you boot a new UEFI system with the compatibility services module, so it looks like it's still running BIOS, you still have a whole number of BIOS interrupts available to you that can still be called from the operating system that still then jump into the firmware and execute code. None of this has gone away. So this is not some new issue. UEFI is not the big concern here. The problem is that firmware has always been this bad, it just matters more now. Where is your firmware? Your firmware is all over the place. There's firmware in your motherboard chipset, there's firmware on the embedded controller, the thing that makes your fans work and makes the power button work. There's firmware in your network hardware, there's firmware in your SSD, there's firmware everywhere, it is everywhere. The firmware is definitely inside the house, it's also outside the house. It's above us, it's below us. There's firmware everywhere. And yeah, there's a lot of firmware. The firmware I'm going to be concentrating on is stuff that is running on the host CPU. But firmware exists in other places, and it is, in fact, demonstrably the case that firmware in other places also has security issues. There was a recent paper published that looked at the security of self-encrypting SSDs. And it's cool. Several of them had magic calls you can make to the firmware that allowed you to overwrite bits of the firmware in RAM, which in cases where they were doing decryption by you giving it a password, it checking that the password was the expected password, and then it unlocking the disk, as opposed to it generating a key based on the password. You could just disable that check, give it any password, and then have the disk unlock. So firmware in a lot of these places is security relevant, even if it doesn't immediately look like it could be that dangerous. System management mode, which I alluded to earlier, is a magical feature of x86. So system management mode was introduced in the 386 SLC, which was Intel's first attempt at a laptop-specific CPU. The reason it had system management mode was so that you could have a timer that would repeatedly trap into system management mode so that it could then turn fans on and off. So even back in history, laptops were trouble. But once system management modes had been used for this purpose, people started realizing, well, OK, I don't trust operating system authors to get things right. I'm going to put code in system management mode, and then my code will run regardless of what the operating system does, and I can make sure everything is fine. This has worked out exactly as well as you'd expect it to. The great thing about system management mode, among the great things about system management mode, so you can't see the code. System management mode, when you trap into it, executes code from an area of RAM that is hidden from the operating system. You can't touch it, which is, in a sense, good, because system management mode is also then in a position to scribble over the entirety of address space. So it's kind of bad if you were able to just modify that code and then trap in system management mode. You could do whatever you wanted. So obviously, it's great that that is literally impossible. It's not literally impossible. System management mode is also privileged, as I mentioned earlier. Once you write protect flash on Intel platforms, if you attempt to switch the write protect bit back off, that generates a system management interrupt. The system stops running. The SMM code pops up, decides you probably didn't want to do that, and write protects the flash again. So that prevents you from, at the operating system level, rewriting your flash. So this is helpful from a security perspective. Good work, system management mode. Unfortunately, there's also a lot of other entry points to system management mode, and those can include things like, well, backlight control on various systems is done in system management mode. There's all sorts of weird cases where you pass some arguments, and then the world stops. Some magic happens and the world starts again. Sometimes what happens when the world stops is the pointer to some RAM that you pass to system management mode, that the system management mode code assumed would always be a specific area of memory that was allocated as BIOS only, instead points at, say, your kernel, at which point you trap in system management mode and your kernel gets overwritten, and its behavior probably changes as a result. So the consequences are hilarious unless it's a system-critical system that belongs to you, in which case it's less hilarious. So I don't want non-x86 platforms to feel left out. ARM looked at x86, and they looked at system management mode, and apparently they thought, gosh, we can do better than this. We can put an entire operating system in system management mode. So Trust Zone is a CPU feature on ARM. It divides the world into normal world, which is what we call a computer, and secure mode, which is what we call not secure. In the normal world, you have your operating system, you have your applications, and you have a driver that allows you to talk to Trust Zone. In Trust Zone, you have a kernel that is running an environment that executes the TEE, or Trusted Execution Environment. Stuff in Trust Zone is not supposed to be accessible from userland. So if you, say, want to implement DRM, you can do that by putting your DRM stack in Trust Zone. And then the keys are in an area where the normal world can't get them, because the secure world is secure. It says so. Turns out the secure world's not particularly secure because Trust Zone is made of code and bugs. So people have found multiple mechanisms for getting arbitrary code execution within Trust Zone. Yeah, unsurprisingly. Different vendors have their own kernels for running in Trust Zone. So sometimes some of the things people use Trust Zone for are kind of interesting. Samsung had an extension of their Knox architecture, which meant that the kernel could only allocate executable pages in kernel space by calling out to Trust Zone and asking Trust Zone to do it. So the idea there being that Trust Zone could verify that this request was coming from a part of the kernel that should be attempting to allocate executable pages, and otherwise it was probably malware and shut it down. Obviously, inevitably, this turned out to be buggy and exploitable. But firmware on your phone, yeah, it's as bad as firmware anywhere else is. Not all runtime firmware is system management mode. You also have a bunch of ACPI code. ACPI is actually not too big a concern, as long as you're not allowing arbitrary people to inject arbitrary ACPI tables. There's a kernel feature that allows the injection of new ACPI code at runtime. If you allow that, then someone can just inject a piece of ACPI code that overwrites your kernel again, or specific bits of your kernel. You can break ASLR that way. There's a bunch of, yeah. Don't do that. UEFI runtime services, you've got stuff like the ability to set variables, which is how you tell UEFI where your bootloader is. And there are various other bits and pieces as well. That's more concerning because that is running in a more dangerous context. It's not constrained in the way that ACPI is. UEFI runtime code can basically do whatever it wants. Management engine. So this one is Intel's fault. Intel decided that having one x86 core per x86 system wasn't sufficient, and recent Intel chipsets have another x86 core running the management engine, which is actually what comes up before the CPU starts running. The management engine gets its own firmware, executes that, verifies potentially the rest of your firmware, brings the CPU up, and then the CPU starts executing the rest of the firmware. These days, the management engine runs Minix. which is an operating system which is made of code. People have determined that it is possible to. So the management engine verifies its firmware, but the firmware contains a file system. It's possible to tamper with that file system in ways that it won't detect until later in the boot process. And someone found a way to modify that in such a way that you get arbitrary code execution on the management engine, which is great. Someone's running, I don't know, probably not a Bitcoin miner on your management engine, because it would really not be very fast, but definitely conceivable. So if you're in a situation where an attacker is able to trigger arbitrary code execution in your firmware, and spoiler, you probably are in one of those situations, they're able to tamper with the entire chain of trust that your system has. They're able to break any of your other validation steps. So firmware security is a big deal. We really need to care about it. So thankfully, over the past few years, while we are still writing bugs, we are also writing code that helps bugs be less dangerous. We have got to the point where we've basically accepted that it's impossible to avoid writing bugs, but we can write compilers that are better at preventing bugs from being exploitable. How much of this is actually happening in our firmware? So first thing we can do in order to reduce the probability that bugs will be exploitable is just to reduce the attack surface. If the firmware never touches untrusted data, then it's much more difficult to exploit security vulnerabilities in the firmware. Well, it's partly by definition. So trusted code is never going to do something malicious, right? Never. So the problem is that we do at some point have to execute some code, because otherwise you have a computer that boots firmware and then does nothing else, which in some ways is the platonic ideal of a computer, but in other ways is not actually what you purchased the computer for. So the more functionality we can remove from firmware, arguably the better our firmware security is. So that's good. Second approach is that we can perform the same sort of mitigation strategies that we do in the operating system. We can put stack canaries there so that if something overflows the stack, we can detect that and end execution. We can use ASLR to put the firmware at random locations in memory when it's executing, so that it's more difficult for an attacker to overwrite specific bits of firmware or get arbitrary code execution. We can make the stack non-executable so that if someone does manage to inject code onto the stack, they're not able to jump into it. These are things that we've been doing on the actual OS level for some time now. Firmware is also beginning to do this. There are definitely UEFI implementations that have all of this functionality, which means it is more difficult to then take advantage of any bugs that exist. Of course, we could just not write bugs. So generally speaking, whenever a piece of software has a security vulnerability that's basically caused because C is security vulnerabilities as a language, someone will pop up and say, oh, no, the problem isn't C. The problem is that your programmers are not sufficiently competent. And a fun thing to do is to then find any projects that that person works on and look for CVEs. Because generally speaking, they're saying this despite having a bunch of high-priority security issues with their code. We are not able to avoid writing bugs. So the best we can really do is reduce the amount of code to the extent that the number of bugs is manageable, build the software in such a way that the bugs that do exist are less likely to be security vulnerabilities, and then also ensure that when we do find bugs, we're able to fix them and provide updates to people so that they can patch the bugs. It's not just about code quality, though. Security issues that are triggered by firmware are not necessarily a result of the firmware having the sort of thing that we think of as a security vulnerability. There's a lot of hardware that needs to be configured correctly in order to ensure that the system is running in a trustworthy state. Not all firmware does all of this. There's a piece of software called chipset. You can grab that and run it, and it will tell you whether your firmware has configured your system correctly in order to avoid security issues. So chipset's cool. Wholeheartedly recommend running that just to see how bad things are. It does involve building a kernel module, so if you have secure boot turned on, you'll need to figure that out. So we can reduce attack surface in various ways. Linux boot is a payload for existing UEFI PEI layers. So the PEI is the pre-EFI initialization step of the UEFI system. It's the code that brings your hardware up and gets you to a state where you can then run UEFI proper. Linux boot is a project that basically takes the existing PEI code and then shims a new layer on top of that instead of the existing Dixie code. And you basically just have your firmware jump straight into a kernel. And then from that perspective, that side of things is quite like the petit boot that Stuart was talking about earlier. You're then able to use Linux, and as we know, Linux doesn't contain any security vulnerabilities. But yeah, Yabbits is a pretty much from scratch implementation of the UEFI spec that is a viable payload for Coreboot. So it's a much smaller UEFI implementation, and less code should mean fewer bugs. An interesting thing that shows up recently is called Project Mu, and this is actually a Microsoft initiative. They are attempting to basically take the Tiano reference UEFI code, but make it more maintainable and make it more agile. They're attempting to do more aggressive security work there with the goal of pushing it back into Tiano. But it's kind of weird. Microsoft released the source code for a whole bunch of the firmware that runs on their Surface devices and pushed on GitHub. 2019 is strange. So right now, Mu is not something you can build as a payload for Coreboot, but it is, so you can't easily take Mu right now and build it and run it on any other systems, but it is an interesting avenue of potentially making things better. Many people say just use Coreboot, and the problem is Coreboot doesn't inherently save us. Coreboot is, if you can build a Coreboot image for your system and flash it, then great. You have the ability to update firmware. You can patch bugs and fix vulnerabilities and reflash it, and that's great. But Coreboot itself is not the problem here. Coreboot mostly doesn't expose any runtime services. Coreboot mostly doesn't handle untrusted input. Coreboot itself, we could write giant bugs into Coreboot, and from a security perspective, it wouldn't matter because there's no way for an attacker to get at that code because Coreboot isn't there at the point where an attacker is able to do something. Instead, it's the payloads that Coreboot launches that provide most of the runtime attack surface. This isn't strictly true. There's some system management mode code does come from Coreboot itself rather than the payloads, but overall, Coreboot itself, we don't need to worry about from the security perspective. It's very difficult to write a meaningful x86 firmware that doesn't use system management mode at some point. Like I mentioned, if you want to protect your flash, you have to use system management mode. Unfortunately, right now, Coreboot payloads mostly don't implement flash protection, which is it's something you can turn on, but then if you ever want to update your firmware, you have to attach a flash programmer to your system and reflash it by hand. You can't then easily do updates at runtime. So yeah, there's trade-offs here. So I'm going to talk about some of the, management engine, yeah. If you have a management engine before version 12, there's no rollback protection. Someone with physical access can flash older management engine firmware onto it, and it will execute that, which means even if you've patched your system so that it doesn't have any known management engine vulnerabilities, someone with physical access can forcibly downgrade the firmware to a version that does still have vulnerabilities. So, unfortunate. One option is to buy a new computer that has version 12 of the management engine. The alternative is, if someone doesn't have physical access, it's probably not too bad, so just don't give your laptops to untrustworthy people like me. So I wouldn't lose too much sleep about the management engine. It's definitely a security concern for certain types of user, but practically speaking, no one is likely to take advantage of these vulnerabilities. The best thing that someone can do in general is just make sure that your system is running the latest version of the firmware. And the Linux Vendor Firmware Service, or LVVS, is a service that provides industry-standard UEFI capsule update files. And several vendors now contribute to this. So your firmware updates now come through can be applied with a similar experience to any other software update. And vendors are also now supplying, on non-Linux systems, vendors are now also supplying their firmware via Windows Update. So we're actually seeing that side of things get a lot better. It used to be a colossal pain to do firmware updates. Now it's just something that happens magically behind your back. Not at all concerning. So as long as your system vendor actually patches security-relevant issues, applying firmware updates is probably good enough. That is something of a presumption to make, but some of them are not too bad at this. If you want to run your own firmware on a system, then what are your options in terms of trade-offs between functionality and security? You can build Tiano, the reference UEFI implementation, as a payload for Coreboot, and then you can flash that into your firmware. And in fact, it's what I'm running on this laptop. So this is an apparently perfectly normal UEFI-based laptop, except it's running a firmware image that I built. So to clarify, I didn't write it, I just built it. Unfortunately, the Tiano payload doesn't have support for secure boot, and it doesn't really do firmware flash protection. So you can choose between either your system is secure against attacks, attackers just reflashing, getting root and then rewriting your firmware, or you can choose a system where you can actually do firmware updates without needing to take your machine apart first. It's definitely a trade-off. So with luck, that will get better before too long. If you are willing to not tie yourself directly to x86, then you have other options. So as Stuart was talking about earlier, the OpenPower platform has basically open firmware all the way up that does have the security characteristics you would probably like it to have. And you can rebuild that yourself and reflash your system. There are various ARM platforms that are, well, a lot of the new interesting ARM devices coming out are running proprietary vendor UEFI stacks, and so it's not straightforward to replace the firmware on them, but there are various other ARM devices where you can basically replace the firmware yourself. Some of these pretty much just run U-boot as their firmware. It's just a jump into here, start executing code, and that code happens to be something that can initialize the hardware, but is also a bootloader. U-boot's not a magic make all my security concerns go away solution, though, unfortunately. I played a little with taking the U-boot file system code, putting that into a small userland test harness, and then building it with AFL, or American Fuzzy Lop, which is a fuzzer that instruments the code and tries to figure out how to change the input in such a way that it runs different code paths. turns out that if you feed the U-boot file system code malformed file systems, you get some interesting bugs. And thankfully, file systems are not something that, obviously file systems are something that can be under control of an attacker. If, for instance, you support booting off USB, attacker walks up, plugs in the USB stick. If the file system can be malformed in a way that gives you arbitrary code execution, any of your other security guarantees have gone again. So it's not ideal, but it is, of course, open source, and you are able to fix these bugs and update your system, or wait for someone else to fix the bugs and then update your system. So in some ways, better than elsewhere. If you have a Chromebook and want complete control of your firmware, then you're in luck. You can rebuild the firmware from scratch entirely. If you want to actually flash the entire firmware, then unfortunately you do need to disassemble, well, on older Chromebooks, you need to disassemble the machine in order to remove a screw that allows you to actually write to the initial bit of flash that contains the initial verification keys for the rest of the firmware, because with luck, you don't have access to Google's firmware signing keys. Just, if any of you do, please let me know. But it's not super straightforward to redo everything so you replace the keys with your own keys, but you can do it. You can rebuild your firmware, sign it with your own keys instead, and then, hooray, you have a complete firmware implementation. More recent Chromebooks, you don't have to disassemble them. There's a physical presence test based on a hotkey that allows you to disable the write protection that way. If you're super advanced, then you have the opportunity to try to run vboot, which is the Chromebook verified boot infrastructure, as a core boot target on a non-Chromebook platform. It's not fundamentally tied to Chromebooks in any way. So I'd be really interested if anybody has actually attempted to do this. I wasn't able to find any documented cases of people doing so, which doesn't mean it hasn't happened. Only problem there is that if you are concerned about physical presence, attacks based on someone having physical presence, then most machines don't have the same setup where you can easily modify the state of the write protect pin on the flash. So you don't have a way of ultimately protecting the initial set of verification keys at the beginning of the flash. So it's not necessarily going to be quite as good as it would be if you were doing it on Chromebook hardware, but otherwise I don't see any reason why you would be unable to build basically the Chromos security model on a general purpose x86 laptop, as long as you're able to reflash it with Coreboot in the first place. So documentation for vboot is there. So I sort of led you here with the vague promise that I'd be able to tell you how to make your machines good and secure. And unfortunately, that was a lie. In most cases, I don't actually have a good answer for you. Most of the options that involve you running open code also involve you making some sorts of trade-offs around security. So depending on what your threat model is, the best approach differs. If you ultimately want freedom, then right now that probably does involve making some compromises on the security front. Upside is you are able to do this in the way that, well, you can fix all the other security vulnerabilities and fix your system, but yeah, the world is sadly not perfect. So that is everything I am going to present. We have 5 minutes or so for questions.
Thank you for an excellent presentation. What are your thoughts on disabling management engine, kind of work that companies like Purism and others are doing? Thank you.
Right. So the management engine is, in general, running all the time. And you can't disable it entirely because otherwise your CPU never boots, which, again, kind of defeats the purpose of having a computer. So the approach that has been taken is that there's a bit you can set that does basically cause the management engine to stop executing most code after it's done system bring up. There's an app called ME Cleaner, which you can also use to remove most of the code that runs on the management engine, which reduces the attack surface significantly. So yeah, that's something you can definitely do. And you probably do get some security benefit from doing so.
Do you have any opinion on the viability of the Supermicro BMC hack that was in the news last year? This is just not whether it actually happened, but whether it was actually plausible.
OK, so backgrounds here. Bloomberg produced a story towards the end of last year where they asserted that Supermicro motherboards shipped to various vendors, various customers, had been modified with the introduction of a small implant that compromised the BMC and then backdoored the rest of the system as a result. There has been very, very strong denials that this actually happened from a bunch of affected people. I am not in any position to say with certainty that it didn't happen or that it did happen. In terms of the plausibility, though, so Trammell Hudson gave a presentation at CCC the very end of last year where he demonstrated a proof of concept implementation of this. He built an implant that is, with a one-wire connection, capable of modifying the SPI data coming off flash in such a way that the BMC ends up running modified code. So it is technically possible. Whether it happened, no clue.
The Intel management engine, you mentioned it runs Minix. Why do you reckon that's the case, and why not something like FreeRTOS or whatever else?
Why is the management engine running Minix? So from some perspectives, when you're implementing something, one of the things you have to care about is how easy is it going to be to continue finding people to maintain this code base in the long run, or to add functionality to it. One of the reasons that the x86 industry went with UEFI rather than just going with open firmware was that it's not easy finding Forth programmers. And it's also difficult finding people who are enthusiastic about learning Forth. So in that case, UEFI was a way of getting C developers into firmware development. So it would not surprise me if the choice of Minix was largely around we have people who know how to target POSIX-like operating systems, and so Minix is a small implementation of a POSIX-like operating system, and presumably the licensing terms were also appealing.
Hi, thank you very much for the talk. Quick question. How well would a hypervisor isolate, say, untrusted code from your firmware?
Depends on the implementation of the hypervisor. So for instance, KVM, somebody running as a KVM guest has basically zero access to the system firmware. So running all untrusted code in a hypervisor like that is, yeah, isolating it, great, you've made the world a better place for yourself there. Something like, but it depends on the design of the hypervisor. For instance, DOM0 in a Zen environment is technically running under a hypervisor, but also has direct access to most hardware resources. And in that case, the hypervisor won't do anything to save you. You could certainly mask off accesses to sensitive resources and basically prevent the code running in DOM0 from being able to touch anything that's released to the firmware. You do then end up with a system that you probably can't use, but you could do it.
Hi, Matthew. Are you aware of any vendors that do a particularly good job of firmware, or are they all terrible?
So I can't really give any strong feedback on that. I know that if you look at LVFS, you can look at which vendors are uploading at a reasonably high cadence. You can look at how far back they're supporting devices. So that might give you a metric that you could use to come to some sort of decision there.
Cool. We've got a small token of our appreciation here. Thank you very much for an amazing talk.
Thank you.